Okay, so now I don't see the button to turn my video on, but let me leave it off also for the bandwidth concerns. So thank you for having me, and yeah, let's quickly get started. I'm going to talk about multimodal AI in medical edge and client device computing. I'm Helena. I'm with Intel, where I am in the OpenVINO team, where we focus on enabling key customers to run medical and other AI on Intel hardware, and we also focus on integrations in other ecosystems. So AI is transforming healthcare and life sciences workflows. It's transforming everything, so of course also medicine. But medicine has some unique challenges. And we see that on the one hand, this is a very fast-moving field with enormous innovations. And on the other hand, these innovations do not always make it to production. So data privacy and security is obviously very important for medical AI. And that is why being able to run state-of-the-art models on local devices without being dependent on cloud services has a lot of potential. For example, for organizations in Europe, not being dependent on cloud companies, which tend to be in the US, is a topic that's actually regularly in the news. So we have heard about how radiologists will be obsolete soon for over 5 years now. And to be clear, I think we're still very far away from that future. But it is a fact that large tech companies like Google and Microsoft have increased their attention for medical AI. A couple of years ago, this was also still a hot topic, but it was more interesting research topic. And now it is more than that. These are key articles on the websites of both companies. And now you may wonder, well, where's Intel in this picture? Didn't you say you were with Intel? Yeah, we'll get to that. So before we go to medical AI with Intel, let's start with OpenVINO. OpenVINO is Intel's AI inference toolkit. With OpenVINO, we focus on making models run well in production. So we don't make new models. You already have a model from either PyTorch, TensorFlow, or another framework. And we allow you to run it on your local machine in an optimized manner. Also on a Xeon server or in the cloud or on specialized FPGA hardware. And there's a synergy with Intel hardware and software. The buzzwords AMX and XMX that you see in this slide refer to specific instruction sets in Intel hardware that are optimized with OpenVINO. For example, AMX has instructions for extra fast matrix multiplications, and that, of course, makes your inference runs faster. And well, most AI development is in Python, and Python is also great for deployment, for example, with VLLM. If you want to create an application for end users to use and just easily install, then maybe C++ or JavaScript is a better choice. And we support all of that. And it's kind of easy to switch. And you can use OpenVINO directly for a super low footprint, but we also have integrations into popular ecosystem solutions like transformers. We'll get to that later. So, okay, the previous slide was a high-level overview. This slide lists my personal favorites of OpenVINO. And of course, I'm biased because I work in the OpenVINO team, but I actually joined this team. I was first in another team at Intel, and I thought, wow, OpenVINO is great. And I chose to join that team. So these are my favorite features. First, I think maybe most important, it has very few dependencies if you work with Python. If you are a Python developer, probably you're familiar with the dependency hell, where you install one thing and then you get an error about this dependency version is not compatible with this other dependency version. And you think, no worries, I'll fix that. And then you get a new error about now a third dependency that is suddenly no longer compatible with the first one. So dependencies are an issue. There are several XQCD graphics about this. It's a well-known problem with Python development. And with OpenVINO, you only have NumPy, so much fewer things can go wrong. Then the features of OpenVINO itself. We have a preprocessing API that allows you to embed the model preprocessing in the model graph. For vision models, for example, you can resize it. For language models, you can embed L2 normalization. You can also embed post-processing. And if you have very small models, this can help speed up end-to-end inference time. But maybe even more importantly, it simplifies inference code. You don't have so much boilerplate anymore. which also makes it easier to switch from Python to, for example, C++, because now you don't have to write all that normalization code in C++ anymore. It's just part of your model. We have latency and throughput hints. So if you want to optimize for throughput, you probably want multiple threads, and you don't have to worry about that. You don't have to be familiar with hardware things. You just set the correct hint, and OpenVINO does the rest. Similarly, for throughput, especially on CPU, you probably want asynchronous inference to max out all the threads on your CPU. But async can be tricky. It is tricky, especially with Python. And you don't have to be an expert on this, because you can just use our async API, and it handles that all in the background. Write once, deploy on CPU, GPU, NPU. That was on the previous slide too. But here's what it actually means. You don't need to move tensors to a device or to manually change precision of the model and the tensors. So you can really write your code once, and it just works when you switch between CPU and GPU. We're truly open source, Apache 2.0, and we have a very easy API. It's just one line to compile a model and then one line to run inference. So no need to get a whole new mental model in your head about how everything works. There's basically a one-on-one step from your source framework to OpenVINO. So these are my favorite features. That was basically plain OpenVINO, and that works everywhere. OpenVINO first release was 7 years ago already, so it's a mature framework. But of course, recently generative AI became much more popular, and now we have OpenVINO GenAI, which uses OpenVINO internally, and it's a package to simplify generative AI inference. It's in that sense similar to what Hugging Face has done for generative AI, where you can, which makes it really easy to run GenAI inference. You don't have to write your own inference loops, etc. You can just create a pipeline and then call it. It works for language models, stable diffusion, audio models, and fiction language models. And it fully integrates tokenization, and also no extra packages needed. Pip install OpenVINO GenAI. That will include the regular OpenVINO package and of course NumPy, and that's it. There's also a C++ package. So again, all the benefits I mentioned before. So, okay, I said it's easy, but what does it look like? Well, this slide shows that. This is the simplest example. I chose an LLM because that's the very simplest, but inference for stable diffusion and vision language models looks really very similar. You instantiate a pipeline and then you run inference. So before you can instantiate a pipeline, you do have to convert the model to OpenVINO. And that's also just one command line. And for this, we leverage Optimum Intel, which is our integration into Hugging Face ecosystem. We have a partnership with Hugging Face for this. So you can export the model and then you run these 2 lines of either Python or C++ code to do inference. There are also a growing number of OpenVINO models on the Hugging Face Hub already, so you don't have to export your model. So I did just say that for me, one of the big benefits of OpenVINO is no more dependency hell. But sometimes dependencies are fine. And if you already are in the Hugging Face ecosystem, you can also use our integration in Optimum Intel to run inference, not just for exporting models. And this is especially easy if you already have Hugging Face code, or if you want to modify existing Hugging Face code from someone else to use OpenVINO in the backend. So this example shows it's just you change the import, the auto model, to an OV model, and then you make the model an OV model, and then the rest of the code just works as expected. So the last topic for OpenVINO. I don't want to get into technical details too much, but I did want to touch upon this. This is the key method that allows us to run these kind of large models locally, and that is quantization. Quantization is reducing the precision of the weights and sometimes also the activations of the models. Models are usually trained in 32 bits or now more frequently 16 bits floating points, and reducing that to 8-bit or 4-bit integer is going from a continuous space to a discrete space, and a pretty small one at that. It massively reduces the number of possible values. So this could be like a very long talk by itself or a whole university course. That's sadly out of scope. But I wanted to touch upon this. I think it's pretty magical that we can decrease the number of values from millions to only 16 and still get pretty good model accuracy. But as you can see in the picture, which shows quantization of an image compression, to visualize what's happening a bit, there are also trade-offs, especially the feed, for example. It's just terrible. If those feed happen to be important, then you will completely miss that in the 8-bit or 4-bit versions. And that's true for both image compression and model compression. So sometimes these details are important and that can be challenging. And there are methods to reduce these trade-offs. So we don't have a linear method to go from 32-bit to 4-bit, as we often do with images. With quantization of models, we have several methods to control exactly how we map the 32-bit space to the 4-bit space. And I listed some of them here. And this is definitely still an area of ongoing research. It's very interesting. Now, finally, medical AI with OpenVINO. So medical AI with OpenVINO is not new. This is a demo that I created in 2021 to show inference on a CT scan with 60 frames per second on a regular Intel laptop, which was way before the era of AI PCs. This also ran on CPU and GPU together. And I still think it's an interesting demo that we could do this. This shows segmentation of the kidneys, which you could then use for further segmentation tasks. This was there are many ways where this can be useful. And it's not just demos, of course. Intel has had partnerships with leading medical companies for a long time. This screenshot shows that GE found that they could detect pneumothorax 3.3 times faster on the latest Intel hardware. I think in these, for these white papers, they always want to see some kind of metrics, but it is... So yeah, here we have Siemens improving inference speed by 35 times, so even better. Obviously, inference speed is important for these kind of applications, and it's only becoming more important with agentic AI and the chaining of models becoming more and more important. Then you don't want any individual model taking too much time. And here we also see the organ contouring, which is actually used by a leading company and not just for interesting demos. So, well, traditional vision models are still very popular by customers and are not going away anytime soon. The hot thing right now, and presumably the path for the future, is multimodal AI. The examples today focus on visual language models, where a vision encoder is coupled with a large language model, which in our case is not actually very large. The models we use are 4 to 7 billion parameters, which run really well locally. If we have a single model, we can also run models up to 14 billion parameters very well locally, but this is the medical models that currently exist. So this slide shows LLaVA model that was created by Microsoft about 2 years ago. They started already with this. And the really great thing about this model is that it can work with all kinds of medical images. X-rays, CT scan slices, just pictures of wounds, histopathological slides. It really is a research model, though. It shows possibilities, but definitely not meant for any kind of production use. Even on the source model, the accuracy is about only 50%, which is obviously not good enough. But it's an awesome start. It's really great that Microsoft made this model available freely as a first of its kind model. and they use Mistral 7B. It would be really interesting to see if they continue with this with newer models. So now I'm going to let me see if I can stop this slideshow and then show the live demo. Do you see my browser screen now?
We see your browser.
Correct. With the Google Med-Gemini 4B demo, right? So I did want to show a live demo, but I was a bit worried about doing this on the Zoom, which is also sharing my screen and everything. So I initially just also entered some values, so I would have something to show if everything crashes under the load of also having Zoom on. So this shows the LLaVA demo that we just saw on the screenshot. Here I set it to explain the X-ray image, and it gives an answer. And as I mentioned, Microsoft is going all in on this. They promise a path to medical superintelligence, and Myra 2 is one of their newer models, which is specifically for X-rays, unlike LLaVA, which is for all kinds of images. And Myra 2 has a really interesting, let me make this a bit larger. Myra 2 is a model that also allows for structured output and specific reports, where you can, which you can see here, the model returns there is a pleural effusion, and it can show the bounding boxes of there that the effusion is visible. And it's it also expects really specific inputs. You can give it an indication and a technique. So this is really meant to be a radiology assistant, more than the other models that are a bit more demo-y in nature. Med-Gemini is a new model from Google. So I have here LLaVA. So we see here the output on Myra 2, where we can see that it's a bit of a brief output, but that is also because I didn't give it the exact kind of prompt that you would get for the structured output. Here we see the Med-Gemini model. It's interesting that this is way more verbose, but in the end, all the models do give the same kind of result. So this also, so let me now see if we can actually do this in a live demo. Here we can, for example, ask so it will probably be also a bit slower because I'm now, well, there it is. Not too bad, because I'm running 3 models locally now, the LLaVA, the Med-Gemini, and this one. So we can open a new image and say, so it is easy to see how this is really attractive if the accuracy issues get resolved for a medical practice, where you could just ask questions about an image and get answers about it. So let me show one more thing. Like I said in the presentation, we have with Optimum Intel, we can just go to the model card and change only 2 lines of code. So that is what I did in this file, where you can see this get sample data. It's straight from the model card. This input post-processing. So the only thing I changed is loading this model. I changed auto model to OV model, and I set device to GPU for local inference. This runs on my NUC. It's a small form factor PC. It's a Lunar Lake, which is Intel Core Ultra second generation. I did not make up those names. It is the latest Intel laptop processor, basically. So now we can run this. I'm running this on the int4 model. I quantize this model to int4 with a ratio of 0.8, which means that 20% of the layers remain in int8 to keep a little bit of accuracy, more of accuracy. And that's this is still the main challenge with medical AI, because as you could see in the slide, it's easy to still see in the 4-bit image, yep, this is definitely still a red robin. So for classification, for example, quantization often works really great. And for language models, it also works great, but the output is a bit different. And then the challenge is it too different? And that's something that's really hard to evaluate. And it's why you really need a doctor in the loop if you were to create actual GenAI medical applications. We do see in general, also here, there's a large right pleural effusion. Well, that's what it said here too. So definitely we get generally the same output, but whether it is exactly as good as a doctor expects, that is still an ongoing challenge. That's where we are now. So this was the live demo. Are there any questions?